следить за тем, что задача будет. Просто Macintosh, правда, имеет если такая штука приключится, тогда тебе придется показывать картинку, что поиграть. Если нет, да, тогда ты просто будешь работать с одной камерой. Знаешь, это не маг, конечно, но как он не будет работать, то... Окей, так. И у нас картинка тоже есть, соответственно. точно, если я могу сделать какую-нибудь капу.
Я перезабрасывали.
Я сделал минус 5, но
Я должен был прийти, во-первых, просто
я сделал запрос. Вот.
morning, everybody, or good afternoon. I hope we will have more people here in some 5-10 minutes, but I will not talk very long. I want to make a small exercise or get us going. We have people here from Poland. What other countries? Lithuania? Okay, so Poland, Lithuania, Cyprus, Bulgaria. Okay, how's good afternoon or hello in Polish? Dzień dobry. Dzień dobry. How is it in Bulgarian? Dobry den. Okay, in Lithuanian. What? Labadiena. Ah, it's like sounds similar to Latin, like Latvian. Okay. Did I miss somebody? It was all. Okay, thank you. So actually today we're gonna have a couple of presentations, and then we have 2 workshops from by University of Tartu. They're very nice workshops. I've talked to people; they're going to do great stuff. And we have a break between 2 and 3 o'clock p.m. And basically we'll finish maybe a little bit before 5. Okay? Okay. So actually the first presentation will be by Dominik Nowak from Poland. He's a CEO from Husarian company, and he will be talking about the robotic platform that they developed for construction. So Dominik.
Hello all, it's very nice to meet you. So, as I was introduced, we make a development platform to help people make internet-connected robots. So think about Arduino or Raspberry Pi, but 10 times more powerful and designed for robotics. Not for everything, but for robotics. Our platform is made with 3 basic elements. This is a hardware. So this is a mind controllers, a controller that you can use to make internet-connected robots. It has got many interfaces that you can use in robotics. So, example, you can connect directly motors with encoders, servos, and many different external sensors and extension modules. To this, together with hardware, we provide prepared by our company embedded framework based on real-time operating system with a C++ API that you can use to make a very reliable software that runs on your robot. So I've got a robot. I'm right now logged into robot on the main room on this conference, and as you can see, this is a stand and my friend and many guests of this conference. And right now I'm controlling through the internet the robot. This is a telepresence robot, totally open source, totally based on our platform, and it can be controlled through the web very, very easily. And let me demonstrate how it works. So, at first you have to log into our platform. Johnny example. This is profile of Johnny example, and on this profile you can log into different robots that are associated with your online account. Of course, these robots has to be made using our development framework. And with all this robot you can make different stuff. For example, let's program this, right? So let's open Web IDE. Create a new project. This project is based on, for example, Core 2 controller. And as I said before, this telepresence robot that I demonstrated is open sourced. So let's see how the source code of this robot looks like. And as you can see, I have access from any place in the world to development framework from any robot based on our development platform. And the source code of this self-balancing telepresence robot is also here. And you have got C++ files with defined control algorithm, HTML files with user interface of this robot, and everything is really, really simple. We were on many workshops when our platform were used by many people the first time in their lives, and they needed only, 2 minutes to start building anything, right? So this development platform is cool not only for relatively simple robots, but also for most sophisticated. So for example, one of the best technical universities in Poland already uses our platform to teach students how to build robots. So our platform replaced Lego Mindstorms. So students now can build not only toys, but something like serious constructions. Of course, internet-based, internet-connected. And they use standard development tools like C++ libraries, ROS, so Robotic Operating System. Everything, these tools can be used together with our platform, and this is really, really simple. So I hope you will use our development platform in your future constructions. And probably that's all. I don't want to make a long presentation because nobody liked this. So please ask some questions to me.
Do you have any questions? But can you maybe show a picture? Do you have a picture of the Robotex actually?
Yes, of course. So you can see how robot looks like, for example, in our store. Okay. So this is 2 wheels, self-balancing telepresence robot, totally open source. It already works, and you can see. Yes, I can control this from any place in the world. You can modify this because this robot uses only 2 of 4 ports you can use to connect DC motors with encoders. So 2 are free to use. We use only 1 of 6 servo ports and only 1 of 6 sensor ports, and we don't use extension header ports. So this robot could be much more sophisticated using our framework. And what is interesting, the CPU in this robot is used only in 3% of time. So that means 97% of time CPU makes nothing. This is because of our powerful microcontroller, that is STM32F4. That was designed for a robotic and automation application. And we made very easy to use API in C++, so building robots is much simpler than before.
So I see that the real value is actually that you can program it over internet and just see what it's doing, and you don't have it physically with you, and you can interact with people next to you.
Yes, this is one of the use cases, but of course our development platform can be used not only to make telepresence robots, but also for autonomous robots. So for example, as I said before, it can be used with ROS, and ROS integrates many software libraries for robotics, for autonomous robots that you can simply use together with our platform.
Okay. Any questions? Yes?
Now, if you don't have time, just stop.
No, we have time.
You mentioned that semi-university replaced something with this platform.
Can you repeat?
You mentioned that the university replaced something with this platform, and they started using your platform. And I couldn't understand.
Okay. So one of the biggest universities in Poland have bought 30 controllers like this, and our controllers replaced Lego Mindstorms on this university to teach students how to build robots. So right now they use this board together with a special adapter to connect Lego Mindstorms elements, and this adapter also can be bought on our store.
So you connect actually the models and the sensors to the board.
Right. So you can remove Lego EV3 board or NXT and use this. So it is relatively simple. You simply doesn't use this and use this. We prepared libraries for most of the Lego Mindstorm sensors and high technic sensors, and all our libraries are open source, and you can easily replace the old Lego controllers with new based on Core 2.
Okay, and when you say open source, what exactly is it?
Board. So we provide libraries to connect LCD screens, sensors, external module. Framework isn't open source right now, but we...
And these are libraries that you directly put in ROS.
This is a very low-level thing. Microcontroller is used for real-time things and communicates with the Raspberry Pi, because our controller can be connected to the internet or to another or to a single-board computer through a special port that is compatible with Raspberry Pi. So I can show you on our stand, of course, how it looks like, but generally you connect this board to Raspberry Pi. You have the special Linux distribution prepared by us, and this Linux distribution talks to this hardware, communicates with ROS node from this board, and you define what kind of robot do you have, and which ROS functions you need to share to another node.
Okay, last question. Do you target this more like communication platforms or more like competing with NATO instruments, for example? Where do you position this? Because you embed Raspberry Pi and at the same time you try to control something professional and you give it to university. So I'm kind of lost where exactly is this platform? What do you use it for?
So,
Okay, thank you. Thank you, Dominic.
thank you very much. Thank you.
I will take this off.
The next presentation will be by Tarmo Saluste from
Okay, hello. So sorry for a delay. Now the presentation will start. So I'm from a company called Shaperize. In every day we're dealing with. Every day we're dealing with 3D printing. We also do 3D modeling, 3D scanning, and we retail in 3D printers, and we fix them and also offer courses for 3D modeling and 3D printing. So from us you can get all sorts of services. You don't know anything about 3D printing and we can teach you, sell you printers, help you prototype, make your ideas from napkin into real life products. Today I have a presentation in Estonian, but I hope it's okay if I do it like I will speak in English, so it's probably no problem. So currently we have this bubble of 3D printing. Well, people are saying currently we can print in almost all materials: glass, metal, clay, plastic, of course, wood, food, organics, and so on. We are teaching also currently in Estonia children about 3D printers are here to stay. So 29 years ago, this quite revolutionary news article was found in. It was okay. Yes. So 29 years. This was brand news. The guy who made Stratasys came into the newspaper that revolutionary 3D printing machines will be everywhere. But what happened? Well, patents. So today patents are expiring, and that's why we're having 3D printers right now. Imagine what kind of printers we would have today if the patents weren't made at that date. And even a few years later, it was quite big hit, and for industry it was really wide adaptive since then. Like manufacturing, and people have been using 3D printers ever since in factories, but not in everyday usage. So 27 years ago, this kind of revolution product came out. This is 2D laser printer that, you know, right now we have in stores. You can buy, everybody has even one at home probably. And this printer cost around $4,000 in that time. And that translates into 6,600 euros at current value with inflations. Okay, going to the present. This laser printer can be bought for 50 euros. Now, what's happening today is we can buy 3D printers for prices of around 2,000 euros. So imagine in 29 years, what will the price be for 3D printers? I hope it will be 50 euros. At present, in the past, there was jobs like, I don't know, anybody knows what job was that? Phone operator, yes. People have forgotten about these jobs. People were afraid that technology will take over and people will lose jobs and be jobless, but technology helps us to advance. And I'm hoping that 3D printers will take over factories, like technology is taking over jobs. And things like micro-manufacturing in local spaces, not using transportation for or logistics for having parts from one part of world to send to another. Things can be made on site. Today we are teaching children. This is from first to third grade children. I'm teaching here SketchUp for them, and it's really they're taking in, because SketchUp program is really simple. It's quite intuitive. It's easy to learn, and even applications programs are still developing every day. It's getting easier and much easier, and these people are our future, and they will know more about engineering than our current graduates from university. And this will mean that if there's access to 3D printing, those future citizens will have like local manufacturing. They will make their own custom parts. They know how to design their own parts, be their own like tailors. In the past, there were tailors where one man made shoes and their children after him made shoes. And in the future, these kind of jobs will be back. There will be more custom-made, do-it-yourself people around. In Estonia, currently there's 25%, well, in ideal terms, because there is 125 printers in schools, but some schools have more than one. But ideally, it's 25% of schools have 3D printers already. And in 2015, September, there was only 5 printers. So over 1 year, the amount of printers have increased tremendously. Another note from past. In '96, there was established this kind of entrepreneur 3D systems, and from that I see that there's a connection with a few other things futuristic that I saw when I was a child. In '97 there was this movie called The Fifth Element. If you know, the main character Lilo was 3D printed. There's images from that, but let's see. And after that, the person escaped. So going back to the present, in 2011, there was first 3D printed organs made. And another note from past, in '97, was a computer game I used to play, where they 3D printed war machines. It was here you can see there was made a ship. In the top corner, there's made a kind of robot. And what's happening today? They're printing weapons already. So and if you have seen the Natural Geographic Mars series, they're also already talking about 3D printers on Mars and local manufacturing there. So we gone from '89, from having 2D printers introduced into offices as a really high expensive things and useful thing to have, to present where we're having 3D printers going to the offices. We have sold 3D printers to offices that have, well, they every day have a prototyping, And in future, you can have 3D printers in any kind of office where they print everyday items, souvenirs, like key rings for their visiting partners, and so on. And with increasing materials and options of printing, sizes go down. I have seen printer which is a kind of a box. It has costs around 200 euros, and it prints kind of small items already. So 3D printers are going small and cheap already. And that's it for my presentation. If you have more questions, you can ask.
Any questions? Because we're leaving the conversation, I have one question. In your opinion, what's the biggest challenge with 3D printers at the moment?
3D printers, well, biggest challenge for me is that people don't know about 3D printers. So we're here at Robotex showing people what 3D printers is, what are the capabilities, what can be made with 3D printers. And the more people learn about 3D printing, the more it will be stable, the more users it will have, then it will be more developed in the future.
Okay.
And also, I think materials is one of the options, but this is rapidly developing, so it's not difficult anymore. Yes.
Yeah. Thank you.
Okay. Yeah.
So the next presentation will be by Martin Rubiska from ProExpert, and he will talk on a very interesting subject about future.
Check 1, 2. So we can start in a few minutes. Just be patient. Mai dau visin na minua.
Okay, so we can start. My name is Martin. I work as a machine learning data scientist at ProExpert. But by my previous job experience and training, I'm actually also an economist. So this is why I chose to tackle this very interesting topic with you here today, because it's about much more than just technology. So I'm not just going to be talking about flying cars. I also want to talk about unemployment, the meaning of work as we know it, the meaning of being human, and what will future societies look like. So, will robots take your job? I can actually already give you a really short answer. If you are a low-wage professional, then the answer is a resounding yes. So, to see why, we have to go a little bit back in history. So, there have been two waves of artificial intelligence in history. So, the first wave started with the invention of computers. Now, computers are really great, right? Computers are good for doing complex mathematical calculations. Thanks to computers, we could put men on the moon, we could figure out how the Big Bang went down, we could build better skyscrapers, but there's an inherent fault with computers in that they can't really think on their own. In order to have these nice calculations, you first need to do a lot of work on your own. You need to input the raw data, you need to define the rules of formal mathematics, stuff like that. It's a long time for a researcher or even a guy in business. So shortly after inventing computers, scientists started looking into ways of making them smart, making them be able to learn on their own. Now, the first approaches of building an artificial intelligence, these revolved around the lines, let's take all human knowledge available in the world today, let's put it inside a computer, and let's hope that it somehow, thanks to its superior math and deduction skills, becomes smart. This didn't really work out so well. So there's an ongoing project called CYC, that is an artificial intelligence built along these lines. And the thing is that CYC isn't really very smart. So when this AI system was presented with a story about a person called Fred shaving in the morning in the bathroom, it got really confused because first of all, it had been taught that people do not contain of electrical parts. It knew that electrical razors do contain electrical parts. So since Fred was holding the razor, the computer got confused. Is this new entity Fred while shaving still a human or not? So due to failures like this, we started looking into new ways of building an AI. So the second wave of AI-based automatization is going to revolve around machine learning. And what machine learning actually tries to do is it tries to unravel the very fabric of human knowledge. We're trying to simulate the human brain. We're trying to imitate human senses like vision and hearing. We're trying to imitate human decision-making. And this is, of course, a really difficult task, a very ambitious task. So all these feats that I mentioned before, like putting people on the moon, these are nothing compared to trying to understand the human brain. As a matter of fact, what most people don't realize is that the human brain is the single most complex object in the known universe. So it's actually the second wave that's going to transform our job market the most. And all this recent explosion and visibility of AI applications around us, this is exactly because of the success of machine learning. So let's take the self-driving car example. Now, in order to successfully navigate a car in an urban environment, what do you need to do? You need to be able to gather and process sensory, auditory data, positioning data. You need to be able to see and classify objects. You need to be able to assess danger levels, make predictions, and make decisions based on this information, all in real time. And this, of course, comes very easily to a human driver, but it has been an almost insurmountable task for an AI in the past. And what I want to claim here today is that it's actually the success of applying machine learning technologies that's the reason behind Tesla's or Google's success in making the cars drive on their own. So actually, I want to show you what goes on inside a Tesla's brain. How do they make it work so well? So here's a picture of an artificial neural network. It's a mathematical model devised in the 1940s, but it's still at the forefront of machine learning research. And whenever you hear of these crazy applications from the Silicon Valley, like GoogleNet or DeepMind, I think there was a recent news piece about a few days ago about DeepMind being 4 times more precise than a human expert at lip reading from videos. So this is impressive, right? So all those applications, they are actually based on neural networks in some way. So how come this math is still so relevant if it was thought up in the 40s, right? It's really old. Actually, the reason is increased computational capacity. So here we see the number of synapses or connections between, between these artificial neurons in the model. So what we can actually do is we can compare the number of these connections to that of an animal or a human brain, right? So here we see that at today's level, or well, at the level of 2015, our best models are at the level of a house cat. So we are at the level of a house cat, but we have self-driving cars. We have DeepMind reading lips. So imagine the amazing applications that we will have once we reach the human potential, which will happen, according to experts, around 2025. So why is this relevant to the job market, you might ask? Because we're talking about unemployment, we're talking about jobs. Well, what I'm saying is that all these jobs that simply revolve around being a human are going to be gone. So cashiers, cab drivers, security guards, baristas, store clerks, other service workers, sex workers, people are building sex robots, call center workers, well, the list goes on. So if you do not contribute on a high enough abstract level with your work, you are in danger of becoming replaced. And in 30 years, we will look back to these jobs in the same way that today we look back on, let's say, lamplighters, call center operators, horse dung gatherers, which is like goes a little bit back, but so be it. So the societal issue here is that many of these jobs that are in danger of becoming obsolete, they are near the minimum wage level. Now, since stability has been shown strongly linked to the wage level, it's really questionable whether all these workers, these simple workers, are going to be able to adapt to the rapidly changing job market. Are they going to get these new and more abstract and better jobs? And this is another thing that's questionable is, are there even going to be enough of these new and abstract jobs? And the answer to both is probably no, and this is why it's sort of inevitable that technological unemployment will definitely increase in the near future. So, yeah. Of course, I am not the only person who has reached this conclusion. And there are actually already a few theoretical solutions that have been proposed. So one of the most prominent ones is, of course, basic income or universal income, which is essentially just handing people money. But there are some other options like shorter working hours, better education, broadening the ownership of technological assets. And I don't have the time today to get into that, but people are thinking about this. What I want to do instead is that I want to discuss how will the job market change for the other people. So society doesn't only consist of low-wage workers. We have mid-wage workers and highly paid specialists as well. Actually, in a 2016 report to the Congress, White House economists predicted that for these low-wage workers, the chance of unemployment due to technology in the nearest, I think it was like 30, 40 years, was 83%. But for mid-wage workers, it was like 30%, and for highly paid specialists, it was only 4%. So I want to ask, what makes them so special, right? What makes them so difficult to replace, and how is their job market going to change? So before we do that, it might be useful to define a few key concepts. So a weak AI or a weak artificial intelligence is a non-conscious AI that is capable of human or above performance in very specific domains. So Deep Blue, which you might have heard of, which beat Garry Kasparov in chess in 1997, this was a very specific example of a weak AI applied to the domain of chess. Of course, today, weak AI is everywhere around us. But it's not really intelligence in the sense that we understand the word. It's essentially just a tool. However, strong AI is a conscious artificial intelligence that is able to at least match human performance over all domains. And this is something that we are not even close to accomplishing today. according to experts, it will probably not happen before 2050, maybe even after that. So this is far future, and today I want to focus more on the weak AI. So my talk is very weak AI centered. This is an exert detection. Pretty much the doctor and the computer, they look at images of tumors, and the objective is to identify if it's cancer or not. So as we see at today's level, our best algorithmic approach is still not as good as a human specialist, a doctor. However, human and AI working together actually are by far the best option. Based on this, I want to make the claim that in the nearest foreseeable future, we won't, mid to high wage workers are not going to be replaced, but they're going to be enhanced by AI. And I want to base this claim on two arguments. So firstly, increasing precision is costly, and secondly, our jobs revolve around many tasks. So what I want to do is, I want to look at this from the perspective of a medical business owner. So the first argument was that if we put it into fancy terms, what I wanted to say was that there are decreasing returns to investing into AI sophistication. So what does this mean? It means that we can probably take this AI approach, which has 7.5% error rate, and we can already today, I think, we can make it more precise. We can maybe improve it to 4%, but this might cost an exorbitant amount of money. It might take a team of 50 brilliant research scientists. It might take a year of research time. And if you want to go from 4% to 3%, this will cost even more. So if this very simple approach of an AI combined with a human, and this is, by AI here, I mean a very simple basic algorithm, if this is so precise, the combination of these two, then there's actually no need to try and invest in something more sophisticated. Of course, you will ask, what if technology advances enough that the most basic algorithm has a smaller error rate than a human doctor? So this might happen in like the next 5 years. So does this mean that we should replace doctors? Well, no, because here my second argument comes into play, that a doctor's job revolves around many tasks. So the actual treatment, diagnosis, analysis, communicating with the patients, also doing paperwork, all those trivial things that we don't even think about. So to actually build near human capabilities over all these domains and seamlessly integrate them together, this is what we would call a strong AI complete task, meaning that it will probably not happen before we have strong AI, so not for a while. And maybe you're not convinced by this, so I want to show you some further examples. So this is a NASA's ST5 antenna. It's special in the sense that this antenna was not designed by a man, it was not designed by a woman, it was designed by a genetic algorithm. So what do genetic algorithms do? Well, they essentially solve mathematical optimization problems, and they look towards many solution paths. They try to pursue the solution paths that seem the most promising. They try different mutations of these solution paths, much in the same way that Darwinian evolution has done over millions of years. And then hopefully, in the end, it converges at a globally optimal point. So this is where NASA's algorithm converged. It's a very peculiar design, something that a human would never think of, but it's whatever was the metric that they used to measure its efficiency, it was by far better than the best efforts of human engineers. So looking to this, can we replace the NASA engineers using some optimization algorithms? Well, no, because the NASA engineers, designing this antenna is maybe 1,000th of a NASA engineer's job. So we are not even close to replacing them. Now, of course, you might not be convinced by this, because NASA engineers are probably like the smartest people in the world, right? And their jobs are going to be the hardest to replace. So let's take a more down-to-earth example. There is a proposed future solution, an exoskeleton, that actually increases construction worker productivity 27 times. So it makes you stronger, more agile, flexible, blah, blah, blah. what I say today is that actually already at the current technological state, we have the ability to build construction robots. So we can, if you've seen the movie Transformers, we can probably build something like that, right? To lay brick and do simple construction work. But if you're a construction business owner, this would be an insane investment compared to the market wage level of a simple construction worker, or even a construction worker who uses this suit and is enhanced by this suit. So again, we are not even close to trying these autonomous solutions. And I'm not saying that we won't get there. I think we will have construction robots in the next, okay, I don't want to say the specific amount of years. So finally, I can't leave my own employer out. At ProExpert, we're actually building a product called Sim Factory. And what this does is it provides a data-driven overview of a production floor for factory managers. And it helps them to make better decisions based on this information in real time. So are we trying to replace factory managers? Well, no, not even close. This would be a far more ambitious task. We wouldn't even know how to do it at this point. So we're simply trying to enhance their capabilities. The bottom line is that the human experience, including our jobs, is necessarily very multifaceted. So some aspects of our jobs are more easily automatable than others. Now, we as workers, we need to be aware of this, and we need to focus on developing skills which are our comparative advantage. We need to focus on building skills which, well, in the age of AI, rather than thinking in terms of which career makes me the most money, we need to think about which of my skills contain multi-domain abstract analytical reasoning, and this is the thing that is going to keep us afloat in the future job market. So what will happen as the weak AIs of today, they become more powerful and more numerous? I think our jobs will take a much more supervisory role. So there will be more of monitoring dashboards, so essentially people sitting behind computers looking over machines. And these weak AIs themselves, they will become increasingly more superhuman. So doing things that domain experts, needless to say, regular users are not going to be able to comprehend. If you have ever used Adobe Photoshop in the past, you know how they added this content awareness tool a few years back. So it used to be that if you have some dirty spots on your image, which you had to clean, you had to manually superimpose the pattern or color from next to the spot on each spot one by one. So Adobe a few years ago proposed a solution where you simply select the part of image that you want to clean, and then machine learning algorithm does this automatically for you for every spot. So this is something that works really well in practice, and I'm willing to bet that 95% of graphic designers have no idea why. And this is how I see the future unfolding as well. NASA engineers, they will be lucky if they manage to build some basic interpretation of why the genetic algorithm has chosen this very specific design. Doctors are not going to even bother trying to read about convolutional neural networks that are actually scanning their MRI images. But this is okay, because in the middle of these superhuman domain-specific tools, we are going to be the architects commanding them. So with our own productivities are going to soar. And what we as a society need to do is we need to build effective redistribution channels so that everyone can benefit from this, not only the clever engineers. And finally, you might ask, what will happen after strong AI comes in the year 2050? And here the problem is that your guess is as good as mine. So for an excellent overview of the threats and opportunities, I will show you later a book by Nick Bostrom called Superintelligence. And there he brings up the excellent argument that once we build strong AI, even if the starting state of the system is that of a 4-year-old child or an idiot, since the system has all of mankind's accumulated knowledge available to it, it has all of Google's knowledge available to it, it will be able to skyrocket past Einstein-level intelligence really fast, and from there on build into a artificial superintelligence, or ASI. So this is something that we as humans, we can't comprehend, because for us, an IQ of 130 means that you're pretty smart, right? An IQ of 85 means that you're a little bit less smart. What does an IQ of 12,000 mean? So for these reasons, I really don't want to predict what will happen after that. You may have seen these before. These are some embarrassingly bad predictions from the past. As this talk is being filmed, I don't want to end up on YouTube saying something like that. So for conclusion, yes, I will conclude. I want to make two remarks. First of all, the beauty of the future is that it's always surprising. So not even in the late 90s could we predict the rise of professions such as UX designer, mobile app developer, drone operator, SEO specialist. So I guess some amount of uncertainty is definitely good, as it keeps us agile and willing to adapt. And for the second point, I want to say that work is not necessarily what defines us. So even if strong AI comes and it takes all the jobs away from us, so no one will be employed anymore, we can still find meaning in arts, civic projects, leisure. So actually the communist utopia that Karl Marx so keenly envisioned in the end of the 19th century, this could very well become a technological possibility in the next 50 years, the so-called techno-socialism. So as a final question, an open-ended question to leave up as food for thought for you guys, so you can think about this today before you go to sleep. How do we, as a society, once this becomes available to us technologically, how do we go from today to there with the minimum amount of pain? So I want to give you some book recommendations if you are interested in this kind of topic. So the first one, as I mentioned, talks about the threats and opportunities of superintelligence. The second one is more about democracies and economics and how is society going to change in the second half of the 21st century. And the final one is kind of technical, but this book gives you an overview how these neural networks actually work. So there are some general chapters in this book as well. So if you want to read about how do Tesla's cars actually drive, how do we have speech recognition today, then you can have a look at this book as well. So that's all for today. Thank you.
One question.
I would love to discuss a lot of topics with you because I would like to have a comment. I think there is a lot of populism among this topic because it's not a matter of robotics taking jobs, but it's a matter of change and people are ready to change. It happened in the past with agriculture, where tractors and robots and so on. So what's your thought on this? Is it really a problem of robotics coming or just because people like Elon Musk are enhancing the leading too much?
Well, as I mentioned in my talk, there are, at least in my vision, there are two waves of this automatization. So the first one, it revolved around the computers themselves. So due to the calculations, you could automate and build these tractors and things. But this, it didn't really replace that many jobs, and you could always get these new jobs as the tractor engineers. But the problem is that the second wave, it's really going to take away these simple jobs that we today, in our minds, they are revolved around humans, like going to a hairdresser. Today, of course, you go to a human. I mean, who would go to a robot hairdresser? That's just freaky, right? But once it's like efficient enough, you absolutely have no need for the human anymore. And this will happen to so many service jobs that I think it's really something new. It's like this hasn't been seen in history before, because how many people today work in services? Like 70%, right? So this is going to be an insane impact. So Elon Musk is a very smart person. So of course he sometimes uses populism for his cause, but I think he's right on this issue. And he's not the only one, even though we showed his quote. But basic income is something that actually, there are some pilot projects already in Europe, in Finland and in Switzerland being tried. And this is actually because of this reason. It's not just like a new way to pay, it's not a new way to optimize taxes or something. It's because of automatization.
This is
So next we will have a workshop by University of Tartu, right guys? I haven't seen you, but I'm also from University of Tartu. So maybe you can elaborate more, a few words about what you're going to do.
Hello, my name is Kermo. This is Harald over there, and we're gonna show a workshop that we're gonna do, and we already have done over here at Robotex to smaller kids in the age of around 10 to 15 pretty much. And if you could sit in the first row, that would be best, because we're going to hand out laptops to everybody. So it's a little bit more hands-on. Displayporti? Ei ole vai? Ei, se ei ole jah. Ta on põhimõtteliselt Windowsi If you're turning the computers on and first blue screen, this one is cracked as well. Opening something, let us know. If your laptop is running out of battery, let us know. We have chargers, we have extra laptops, so we can change everything really quickly. This one doesn't work. Okei. Jah, siia ühte on vaja. Here we go. Anybody else running low on battery? No? You too? One laptop for you as well. Here we go. Here we go. Harald, kas meil flaiereid on või? Okei.
kursusleht see on eesti keeles. Kas nagu sellest arvutist ei saaks lihtsalt minna seda kursuslehed, kui me näiteks digisparki peaksime näitama. Samas vahet pole väga.
Vist ei ole jah. Okei. Awesome.
Keegi läks restarti ise.
Nii. So everybody got their computer running, right? Awesome. So let us tell you a little bit about us. To start off, my name is Kermo, like I said.
And I'm Harald.
We are both students from in University of Tartu and studying computer science. It's our second year, and we are as well like kind of student activists or yeah, something like that. So we're doing workshops for younger kids in middle school, high school, and trying to get them excited about programming and computer science. Like Martin said before, that a lot of easier jobs are gonna get replaced pretty soon. So computer scientists are always needed, and a lot of future is tied with computer science. So this workshop, we can't connect a big monitor, so we have to show it to you on our little laptop over here. But this workshop is mainly for 3rd to 5th or 6th grade, and it's just to get them, let them know about different functions in Windows, and get them a little bit excited about trying out different things and figuring out the solutions themselves. So for the and the name of the workshop is called fun way to troll your friends. So it's a little bit mischievous, so but nothing illegal. And we're not going to mess with your Facebook account, so don't worry about that.
All the things we use are built-in Windows functions.
Exactly.
So you don't need to install anything.
So to start off things, the first function that we're going to show you guys is opening up a new desktop on your Windows. Has anybody heard of it before or tried it? Good. So if you have like tons of important and useful things open in your computer, for example, you guys can try as well, like open your browser or Word or Excel or something like that, just to show how it works. And if everybody has something open, then the buttons to press are
Control, the Windows key, and D as delta.
So what it does, it seems like everything is gone from your desktop, but what it actually does is make a copy of your desktop, so you can switch between desktops, pretty much like you have desktops on your smartphone. You can just scroll through them. And to check them out or see all the desktops you have open, it's
Windows and Tab.
Windows and Tab key. It should show the two desktop images that you have open. Some of you may have more from the previous workshop that we're in, but yeah. Everybody got the idea of it? Got everything working? If you don't, if you lag behind or don't understand something, you can ask us, and we are here to help you guys. So the next thing we're going to show you is changing the direction of your screen. So, for example, a lot of at least older computer users don't know the function that you can actually turn the side of or turn the screen sideways pretty much. And the reason for it isn't to watch movies on bed or something from your laptop. It's actually a really good function to write essays, for example, if you can turn your big monitor sideways or write code on your computer, so much more text fits in your computer screen. Anybody knows how to do it? Can you let everybody else know as well?
Control, Alt, and one of the arrows.
Exactly.
Right.
Exactly. Control, Alt, and the arrow keys. Mm-hmm.
Now we have to return it.
Yeah. All the different arrow keys turn the screen different ways. So try to find the right one back again.
teeme selle left alt ja shift, see muudab kirjutamist.
Left, mis asi?
Left alt ja shift, stopp, niimoodi. Left alt, siis kui tuleb meil selline.
Oh. So another function built in Windows is easy shortcut to change languages, typing languages on your computer. So, for example, if everybody could open a Notepad in your computer, just press Windows key and type in Notepad. And to try it out, press
Write something, like anything.
Perfectly right now, right? And if you press
Left, Alt, and Shift, and try to type the same thing, for example. You should get a totally different alphabet. If we have programmed it to be Chinese at the moment. And if you press the left, Alt, and Shift again, it should go to, I think it's India or something like that. Shift again, it should go back to the normal one.
These are just like some of the reasons why you shouldn't, never should leave your laptop open or logged in a public place. So, anyone know what's the quickest way to log off your Windows account? It's much safer than leave it just the way it is. So. Another cool thing about laptops is using numlock. Everybody knows numlock. Desktop computers, right? Like press the numlock and side numbers don't work right. And press it again, they start working again. But in laptop, it's much different. So if everybody has their notepad open, press function
L or M, you can't use it because the numlock is on and you just type the number instead.
So could anybody tell me what time it is right now?
Looking from your computer.
And the way to change it or to turn this function on is settings in Windows. So it can be pretty hard to find the solution again. Like we were trying to fix it as well in the last show, and it took us 10 minutes, and one of the students actually found it before us. So if Harald can tell you about it, how to change the settings and how to turn on the function that the clock would say something else.
So you go to the clock and press right arrow, and the second from the top is it's sea kuupäev, so it's in Estonian. So it's to set the time and date. Press it.
Sorry, all the computers are in Estonian because most of our clientele is in Estonian.
So when you scroll at the bottom, there's täiendavad kuupäeva and it's the second from the bottom. You click it. So the last one is area, and you go to the second one also. Good? Yeah. And can you help them?
Mm-hmm.
Okay. Okay, cool. And over here, when there's AM and PM usually, you can write whatever you want.
Oota, üks second. I guess we missed one of the steps.
But here you can see that.
Windows, and you can see as well that they don't take much time to change your settings. Or I'm going to show you something a little bit more advanced. These little devices pretty much looking like mis on mälupulk, memory sticks. And it's pretty much like 2-3 euro little computer. You can program it, and if you put it inside of your computer right now, it has 10 different functions programmed on it. And okay. So it would like normal case on top of it. It looks just like a memory stick or USB drive. So, and you can cause a lot of trouble with this.
So yeah, they're harmless, but you can put viruses or whatever you want on them. Mm-hmm. You can make lots of damage.
Yeah. And if you're interested about learning more about the DigiSparks, in our web page, courses.
.ut.ee, I'll show you.
We don't have a blackboard over here. kirjuta lihtsalt notepad'i ja siis pane mingi full screen'i ja siis font 70 või ma ei tea. We have examples as well about the code, how to do it, a little bit more information or more different ways to troll even with Windows. And noh, kas sul net on või?
Tal on küll, jah. Sees oli ka. Ja siit oota, siia saab panna kids.
So the computer or the web page is Harald is going to type it on the computer as well, or the screen, big screen. vaata, pane inglise keelde ka. So this is the page that we use for kids and young adults, just to get them. Oh, I guess it's not in English at all. So you can see as well a lot of different things where they can go. It's all free. Check out all the different websites that are linked over here, Code Academy, Code.org, and so on, just to get them a little bit more excited. And there's a place over here about trolling and the DigiSpark gadget. But I guess that's pretty much it for like I said, all the technology is getting cheaper and cheaper, so everybody can keep this as a present to show their family and friends and co-workers, or troll them a little bit, put it in their computers. Huh? Yeah, it's written in C, so you just have to pretty much write the new script on it.
And over here you can see the script that's on there as well.
Mm-hmm.
Do you have any questions? On seal inglise keeles ka?
No. Anname neid kuradi pastakaid. Ei, meil on homme ka. And one more present and a little bit some marketing thing as well. We're gonna give everybody a pen that is actually a smart pen, so the other end is for smartphones and tablets. And thank you for coming, and I hope that we filled your hour interestingly. Aitäh.
So now we have 1 hour break. Let's be back here at 3 o'clock. Okay, welcome everybody back from the break. There are not so many of us yet, but as it was before, I hope people will gather. And I'm very happy to give stage for our next presenter, Markus. He's from Robotex Design, and it is actually one of the biggest and oldest engineering companies in Estonia. So I think there's a lot of good knowledge we can hear. So please.
So, as was mentioned, my name is Markus Kasak and I'm from a company called Robotex Design. I'm here to talk about the innovation. At first, I will answer some questions who and why, especially who are we as Robotex and why I chose such topic. We are an engineering company which was founded in 1998. In Estonia it means it's quite an old private company, and we have about 20 people and 75% of them are engineers. So we are engineering company through and through. We are mostly focusing on electronic product design services, which I will cover a bit just in a moment. And we try to provide design from concept to the real manufacturing for the clients we have. We do have customers all over the globe, mostly in Europe, and circuit integration, PCB and layout services. And the last one is always a controversial topic because software guys tend to say that FPGA is hardware and hardware guys tend to say that it's software. But as a software background myself, and because VHDL, for example, is hardware description language, I would say that FPGA is hardware. Now, we also do the software design where we do from the bare metal programming of the microcontrollers to the whole integrated systems where we have embedded operating system, server communication, and everything between there. We also have tackled real-time operating systems and solutions for different purposes, but most of our current solutions have been done using either the bare metal programming to the microcontroller or custom Linux firmwares. As I said, we try to provide the whole product for the client. That means we also have the in-house capability of industrial design. And here are some examples of different devices we have done. This, for example, is one ticketing system used in Estonia, and there are several others. The point is that when the customer comes to us with an idea, we start from the prototyping phase, and then we go over all the steps behind that, and that's also why I wanted to talk what happens beyond the prototype and what are the challenges there. And from the manufacturing point of view, we do have some prototyping equipment in-house and also small-scale production, but we have partners for the larger quantities. It seems that the video I put there hasn't come over, but you can use your imagination. So, why I'm talking about beyond the prototype? There are several reasons. We do work quite closely with different startup clients who usually come to us with their idea, and it has some kind of prototype form, and they want to just let's go to the manufacturing, let's start to make the device. The other point is that we do have a couple of joint projects both in the EU and also in Estonia, which are also covered by this Estronics cluster, which we are part of. And we have quite a lot of feedback from market, from different projects we have done during the years. And all these show that in a common knowledge, especially when there are young and eager people, the phase after the first prototype is severely underestimated. And the other reason I'm talking about this and I'm talking here is that we are keeping close partnership with different student initiatives, and we are also and always very eager to work with young bright minds. For example, we have worked closely, and some of their former team members even are our engineers now, with a former student team Tallinn, which is an electrical formula racing series, and they have been quite successful over the years. We also sponsor Robotex, and if somebody is interested, we do have a booth out there where we have all kind of different devices which we have done. And we have participated in Back to School project where people who are already in the work market, they go back to school and teach the children and try to initiate interest in different fields. It's this topic. Now let's answer the questions what and what. More namely, I would like to start with the question, what is innovation? I think that different people have a different definition for that. I chose one of the most generic, which comes directly from Latin and is from Merriam-Webster, which is introducing something new. But from the business perspective, I would say it's important to consider this second definition. The process of translating an idea or invention into good or service that creates value or for which customer will pay. Yes, innovation can be done, and it's other great innovators, but the important bit for me and for all of us in Artec is the deliverable part. Because quite usual with startups or with student projects is that the innovation is regarded the part of the idea and new cool solution, and the steps what to do and how to get to production are not so well thought out. So, what are the challenges? I think that if I would go into detail, I could talk until tomorrow. But basically to say, of course, again, there is a business side, but since it's quite different big can of worms, I will leave that aside. And since I do have engineering background, I try to focus more on the engineering and organization or the work management side of the challenges. For example, every project or every device starts with a team of people, and the first challenges are the communication and also how do we organize the work. Usually very different project management techniques are used, and usually sometimes they are used even for the sake of coolness factor. Agile was one that has gathered much of stronghold and is in its essence a very productive way of doing things. But people usually forget that Agile doesn't mean that things are not organized or things are chaotic. Agile usually means that you have to plan even much deeper and much more than with a usual waterfall or other methods. And all kind of team leading and motivating is also part of those challenges. Then if we move to the other point, then I purposefully left out the idea because I expect that somebody who has already a prototype has an idea. But now if we are talking about making this prototype work, get this idea working, then starts quite a severe research phase. And there is very hard work of choosing the balance between different items. For example, typical balance people know is the price-performance ratio. What components do you choose to have the? It should be very fast. It should be very. It should be very marketable at that way. But usually, when the price is high because of that things, it's definitely a drawback. But then again, there are questions of power consumption, about temperatures, about the availability of components, what is their end of life, and so on, and so on, and so on. And when making the PCBs and design, a lot of problems that usually, for example, the impedance, for example, the length or the symmetry of the lines, most because I have a software background, all kind of software architectural issues and also the trade-offs and balance questions. For example, on some smaller items there is a question whether I should use operating system or not. Whether I can make this work straightly writing code to the CPU, or what kind of stacks will I use. If I use a microcontroller, will I have external Wi-Fi stack for that? Will I have external TCP/IP stack for that? And so on. And one of the largest challenges is usually when the first run is not very well tested on wide variety of conditions, then startup starts to see failures on field in quite numbers. Usual is that this goes already back to the component research part, and for example, temperature ranges, the moisture that condenses into the device. There are a lot of potential problems related to that. For example, we have to and must be able to update all the units on the field, because if anything fails with that firmware update, it's impossible to change out all the devices at once. And there are very many things to consider regarding that. To move on, I just chose two case studies which I thought I will talk about a bit, and then I would gladly discuss all these items in more detail with you if you are interested. The first case study is muscle tension measurement unit that was designed for a company called Myoton. Its main purpose is to non-invasively understand the condition of muscles. And when they came for us the first time, they did have already a couple of prototypes. But the problem with those prototypes was that they worked using a gravity, which meant that you only could hold the device on some certain ways. And the main thing that was to add or to innovate on this device was to be able to measure at every angle and also even in zero gravity conditions. So the main challenges here started first day. The component research, for example, was very difficult. At last it was resolved that it's a dual processor design, which has the one main processor for the UI and non-real-time critical tasks, and has separate, and we also had to go through very many iterations. Then the other very just to the right and repeatable and measurable way. And then once we got also, of course, make a lot of different prototypes casing, and not only because of design but also because of how convenient it is to be held when it's used on different positions. And big problem was power saving, because once everything got to get working well, the battery life wasn't acceptable for client, and so a lot of optimization went into the both graphical user interface part and or the CPU that drives this operating system, embedded operating system part. And also with the microcontroller we ran to the limit that because the high precision was needed and the analog to digital converters proved not to be so precise as needed, we had to even write the parts of the code in assembly language to get the wanted performance and to get enough measurements to make good calculations based on these. The other case study is a digital signage system for Estonian National Museum. It's quite a big building in Tartu, 200 kilometers from here, and they wanted to have, instead of ordinary papers, to have the signage not on the TFTs but with e-papers. We deployed 600 devices and over 800 displays there. Here are some pictures of how it looks inside, but what I wanted to show is that here are some examples of the devices that we made there. Again, the challenges were to get NFC antenna working within, all integrated into one PCB, to choose what is the right type of NFC card to have the good distance reading through the glass stands and so on, to have the small footprint on the microcontroller firmware on the unit itself, and to have it all worked and managed centrally from the server side. And the other big challenge was just to get this all up and running from the organizational point of view. So what we have learned from this? The first thing is that trivial truths matter. There are a lot of sayings, there is no silver bullet and so on and so on, and 80% of work or the last 20% of project requires 80% of work and so on. We have learned that these truths must be considered every time. The other thing is that team is the key. Without right team, there is very hard to achieve something. And team without proper environment usually fails. This includes all the organizational part, as I mentioned, the product management and even the tooling and possibilities to prototype and so on. And we still have a lot to learn, but I hope we can also teach something. And the last but not least is that the devil is always in details. There are lots and lots of details, and usually there are a couple of devils hidden somewhere there. So thank you for listening. I don't know how we are with time, but
We have some time, but thank you very much. Any questions? Yes.
you are talking about Newton. Yes. Yes. They were aware of the main problem. They wanted it to be able to measure on all distances. For example, I didn't mention before, but this device has gone through the parabolic flight tests for the zero gravity testing. And there has been some news. I cannot confirm it, but let's see that there is a possibility that in upcoming years they are able to use it in the International Space Station. But talking about other challenges, yes, usually at least half, if not more, we have to map ourselves. And that's something also where experience is very useful, because some problems tend to repeat from project to project.
Yes. The other thing is when they come, they know the problem.
Yes.
So they did get the patent, and they came to you for design. Was the patent formed before they came to you or after?
It's I think the patent for the technology or the principles of the thing were before, but the exact solution was worked together with the client and also with some partners and with us.
But for you to work in all kinds of ways, you got to, for example, change it a little bit, or file a new patent, or a third patent, or a fourth.
I must admit, since I have looked at the project mostly from the software point of view, I'm not very aware what's exact the case with the patents there. But I think that can be searched out and, and looked over if you're interested.
As I get it, you're mostly a business-to-business organization, so businesses come to you for...
Yes. Our end customer is business who has their own customers.
Yes. Have you ever tried to do a consumer device for the end customer?
Not exactly consumer, but we have done thin client computers which had no moving parts when this was rare. And we have done those handheld readers for logistic sector, but then again, usually, I think the thin client was one where we had individual people as customers. In a Digibox, when there was a time when Estonia went from that on for the end customer.
Okay. My question is actually, I'm trying to understand what's your experience when you do something for the end customer. How do you manage to, let's put it in this way, to fight with the larger manufacturers? Because it's an end consumer device and it's probably easier and faster and cheaper for someone larger and bigger to manufacture it. and it's already on the market, what do you do?
We do not directly compete with large volume products. We are usually looking for something which need something extra, something special. That's not covered. Yes, we can say it's our niche markets, but some niches may be quite sizable. So it's if we are talking about making things for the end customer, but then again, since we do have limited number of engineers, we have moved more and more towards making the device for a company who will handle their marketing.
Thank you.
Welcome. Yes.
How long does it usually take to perform testing and the verification of the product, comparing with the development phase, for instance?
If we're speaking about timeline, then it of course depends very much on the product. The whole development cycle, 1 year and a half. That means from the first sketch on the paper to the actual production from the manufacturer. But it's the different phases have been different sizes depending very much of the complexity. For example, this museum project had a quite a lot of iterations of technologies and prototypes to get it work as intended.
But did you test the product by yourself, or did you outsource it to some other companies?
Do we have our own products? That depends on volume. On smaller volumes, we have basically when we make a device, we also make the test system for this device. And if the volume is in thousands, then the testing is done using this test system in the factory, in our partnering factories. But the other, there are several instances of these test systems, and usually a couple of them are of course in our own site, and for smaller volumes, I would say up to 100 maybe we are testing ourselves, which are smaller runs.
Thank you.
Any more questions? Yes. So, would you like to say that you are trying also working as a part or startup accelerator company financially? You can consult with them and you can offer and say what would work and what not.
We are not exactly like hardware startup accelerator. We are more like want to empower the people. But yes, we can say that in a way, because, for example, there is a event. Put your ideas and the best ideas. To get their idea and their prototypes really interpretable. Thank you. Yes.
Okay, good afternoon, everyone. I'm happy to be here representing Skeleton Technologies. So we are an ultracapacitor production company in Estonia, located in the other side of the city, but not so far. And what I would like to talk about today is Skeleton Technologies in general as a company, and describe the Skeleton team. And I think that my aim here is to convince you that ultracapacitors as a technology could change your world. And as engineers, if you will be involved in development of different kind of systems or applications, then ultracapacitors could play a role in this as a high power enabling technology for electrical energy. Company in general has been named amongst the global clean tech 100 companies, and it was founded in 2009. The technology itself is based on patented material, which is a carbide-derived carbon material. This was already, the studies, scientific studies on this material already happened before the founding of Skeleton in 2009, and the patents come together with the part of the co-founders of the company. So ultracapacitors in general are energy storage technology, just like batteries. I will explain what's the difference finally from the product point of view and then also application point of view. Currently we have approximately 70 employees, and we are in quite fast development phase, so it's hard to keep a track on how many people work at Skeleton today or how many are there tomorrow. Skeleton has received investments in 3 rounds in about 26 million euros. And mainly here I can mention UpInvest, Harju Elekter, Kikino Energy and First Floor Capital. Location-wise, the industrial scale manufacturing facility is in Dresden area. The progress is happening in Viimsi in Tallinn. And also we have assembly facility for single-cell ultracapacitors as well as module and system-based level assembly. And in Finland we have a small R&D laboratory also. So Skeleton Technologies as ultracapacitor producer has one main difference, which I already mentioned, is that we start from material level up to system level. So initially, of course, we started producing ultracapacitor single cells. So now the industrial cells are cylindrical type of ultracapacitors, and for customized solutions, we also produce prismatic cells. And from the value point of view for the company as a product, of course, it is much reasonable to also develop modules and systems so that we can really already get to the client the full solution, not only the cells, and then advise on how to use them to get the best out of them. And about people at Skeleton, we have different R&D teams. My own background is in electrochemistry, so maybe at a robotics conference I don't know all the very specific details about electronics and mechanics, mechatronics and so on. I know more about electrochemistry, but today in the team which I am leading, we have mechanical engineers, electrochemical engineers, so we are mainly focusing on the cell level development so that we would be able to increase the energy density, power density in the cells, and it involves also material development. Chemists, chemical engineers, material technologists. And when it comes to modules and full solutions, then of course a lot of electronics, mechanics, electrical drive engineering company, the value is not just working on something interesting, but really if you see anywhere a presentation about companies, people speak about the culture. So you want to join a team where you have the same kind of drive, the same kind of values. So at Skeleton, obviously the mutual aim of everyone is finally to help people save energy by using our products. And in order to have the really efficient teamwork and everyone on the same page, then the culture is based on 3 main core values. I'm not really supposed to maybe say this word out loud here, but this is the way it is, that one of the core values is get shit done, which means that we really try to learn through doing things, not just discussing on things that we could do or how to do for ages. Yeah? We just have a goal in mind and try to do it as quickly and as good as we can and learn from the process. The second core value is pushing boundaries. So if we want to deliver good products and really to develop quickly, then it is important to get out of the comfort zone. And of course, in the process, we always have to use good judgment. So in general, we value always clarity in every process over cleverness. So good development process has to be very transparent and clear and so on. So yeah, these values go from recruiting to, and now getting closer to the technology and the products. So everybody knows that energy storage, so one of the options are batteries. And I think every one of us here, we are very much dependent on this technology. So we use batteries every day in phones, laptops, cars. So this industry is rather mature already, and you can see the comparison here also that in 2015, battery industry value was about $60 billion. Supercap or ultracapacitor industry value was 100 times less. But the predictions for this market growth is really basically 10 times in 10 years, which concerns then ultracapacitor-based solution market growing approximately 3 times, and also the component market cumulative annual growth rate is expected to be around 30%. So this market really is in the growing phase now, and our clients, we see also that are more and more starting to realize what are the benefits of the ultracapacitor technology. So a little bit more explanation, what's the difference finally, is that batteries use chemical energy or chemical reactions in order to get the electrical energy out of it. So more correct term is electrochemical reactions. Ultracapacitors, in this device, energy is stored in an electrical field. Electrical double layer is basically a purely physical energy storage process, attraction of opposite charges. And this difference in the storage mechanism itself is the reason why batteries are able to store a lot of energy, but chemical reactions have barriers when it comes to the speed of releasing this energy. So when it's physical process, as it is in ultracapacitors, it is much quicker. So here is the main difference. Ultracapacitors store less energy, but are able to release it almost instantaneously. So very high power devices. Discharge cycles for and what is special in the ultracapacitors at Skeleton Technologies is that I'm a chemist, but I'm not going too much in detail here. That I mentioned we have this carbide-derived carbon. So It is just the kind of material synthesis process which enables to really fine-tune the material parameters so that we are able to accommodate a lot more energy in the same mass unit or volume unit compared to commercially available other types of carbons, which other producers also use. And finally, when we combine together the material engineering, mechanical engineering of the single cells, and all the other factors, then we are able to get much higher power density ultracapacitor single cells than actually any of the competing companies in this field. So example here is that Maxwell is, I think, the market leader when it comes to volumes. And for the same power output of an ultracapacitor, you can see here that the mass and the volume of the capacitor is roughly 3 times less than the competing product. And if you think about application in transportation or any non-stationary application, then downsizing the system can be quite an important factor. And as it's Robotex here, before going to the applications, I just wanted to bring an example that even in our production, we have also, let's say, robots involved. So in one of the assembly working stations, we have a robot hand, which can make sure that things are done very precisely in the preparation and in the process of laser welding, for example. So we are dependent on robotics much in our production. And when we go to the applications now, then I will bring just a few examples of why we should use ultracapacitor-based systems, what's the benefit. So one example is when you have huge warehouse areas and you need to deliver packages in the right locations and bring out the other ones, then the system, quite often, robots are used there, basically. So for carrying the packages. One option is to have to wire all of the huge warehouse area so that, like the trams are on the streets going on, you get the energy that you need all the time. You are connected to the grid. But it is maybe not the most convenient option. So another option is to use energy storage in the robots. And there you have the two options, either battery or ultracapacitor. With a battery, you are able to work for several hours, this kind of robots. But after working for several hours, these systems also need to charge for several hours. When it's powered by ultracapacitors, then it can be 24/7 operation. So the charging time is in the range of seconds. And as I mentioned earlier, the cycle life is up to 1 million cycles. So it means that really, if it is constant operation and this kind of long cycle life, then this kind of robots can be useful for quite a long time without any maintenance needs. Another example, hoverboards. So there are also different types, but on this picture here, it is also internal combustion engine based hoverboard, so it has the propeller system. And what are the moments when this kind of devices need the highest power? One is startup, and then lifting up. So this is the moment of basically power peak. And if you use ultracapacitors there, then that's the moment, when you start the engine, and you can actually downsize the system just due to this, that you don't need at the constant working time that high power. Again, compared to batteries, I'm not trying to kill batteries here. Actually, I have to say that in most applications, they are complementary systems. So you're not trying to replace one with another, but in some cases you can. So I'm not really against batteries, really good systems. But in this application also, just to have the same power output, the battery system would need to be bigger, which means that it weighs more, and so on. One of quite early clients in Skeleton history, 2011, I think, European Space Agency chose Skeleton customized cells as the ultracapacitors, and we have the module development also. These satellites should go up on orbit in 2018, so not so far from there. And here the function of these ultracapacitors is basically to voltage regulation on the satellites, and it halves the need for conventional capacitors for filtering. And also there are batteries on the satellites, and again, if we use ultracapacitors for the peak power, we can extend the battery life because we are not trying to push the limits of the batteries. And compared to other producers or other technologies, of course it's customized cell, then the internal resistance in the Skeleton ultracapacitors is a lot lower. So again, allowing higher powers in a smaller system. When it comes to transportation, I forgot to mention this on the market growth slide, but if you saw this, then the main sectors are transportation and then industrial applications. So in transportation, one of the key applications is KERS, or kinetic energy recovery system, which enables energy savings up to 20–30%. Of course, depends on the use. And here is an example of truck system. So simply said, during braking, the braking energy is transformed into electrical energy stored in the capacitor, and this energy is used during acceleration. And it can be applied basically in any type of vehicle. So trains, passenger cars, maybe for passenger cars it is a little bit too expensive, but in motorsports also it is quite important to downsize other parts of the system also and have fuel savings. Yeah. And another example for transportation is start-stop systems. So these are already in roughly 3 million cars, which are like passenger cars then. For example, Renault, Peugeot, Mazda, they are using in some of the models already ultracapacitor start-stop system. So this is, again, as I mentioned, basically not to push the battery to the limit and to extend battery lifetime. So these are complementary systems here. And if we take a look in medicine side, then MRI is one of the fastest growing medicine equipments in this market. And MRI machines need very short term and very high pulse power. And for this, even hospitals need some special generators and so on in order not to cause some problems in the grid, just due to these power pulses. So here also ultracapacitors could take this high power load. And I'm not going in more detail here. I will wait for your questions. There should be nice pictures here. But yeah, in grid level for renewable energy storage, so these are already some megawatt containers. Ultracapacitors can be used there. Power quality control UPS systems instead of batteries also, so it's very quick reaction of the system, so instantaneous power, there is no lag time. And in different types of industrial equipment. So yeah, if we are at Robotex and I'm a chemist, then what was my first thought about this? Like, what will happen next? There is no picture. It's supposed to be a transformer, and it looks really as if I'm predicting end of the world. That was not my idea, but luckily you're not seeing this. But yeah, this is something which came to my mind, that ultracaps could be used in transformers. Yeah. Okay, thank you.
Okay, thank you. Questions? Yes?
I have a question about the technology. So if you would like to store a lot of energy, you can take a number of cells, attach them together, but with a single cell, how much energy do you have an upper limit with the material that you use?
I can give you the numbers per volume, basically, yeah. So the highest energy density is about 14 watt-hours per liter.
But you can theoretically build a cell from 100 liters or 1,000 liters. Is there a boundary there?
Yes, this is the material part here also. That yeah, if I want 100 watt-hours, then I can have it, but it's not per liter. Yeah. Anyway, so this is currently really the limit when it comes to volumetric energy density in single cells. Yeah. If you build a module, you can do, yeah, you can design it as you want. Are there any production cars? Ah, well, I would not answer this at the moment. Yes.
Yes,
How many capacitors are you producing per year?
We are in the growing phase now, as I mentioned earlier. So I would need a production manager here at the moment.
I mean, like producing CDC is quite hard, so
Yes.
when you,
True.
it's a tough environment, so.
But anyway, then answer to your question, depending on if it's larger cells or smaller cells. By the way, I'm showing pictures, but there is also a skeleton box here, so you can go there and touch the stuff and speak to my colleagues and ask for more stuff. But yeah, I might be lying, but a few tens or thousands of cells. I should have rechecked this before coming here. Yeah. Sorry?
That's a lot of coordination then.
Yes, for CDC, yeah.
any other questions? Yes.
What happens when you short the contacts? Does it set the building on fire?
With a single cell, you can have a few sparks and maybe some small aluminum pieces flying around. Has happened several times. When it comes to module and it's a charged module, then better not to short circuit it. Yeah.
So do you have some safety implemented in the modules of the future?
In modules, okay, in general, of course, there are control circuits which are avoiding this, that any cells if there happens some damage, that you wouldn't have overcharge and so on, yeah. And basically, yeah, if there is some short circuiting or problem, but from safety point of view, of course, for modules, you need to have. There are many regulations for this, that you have to avoid this kind of accident. But if, for example, someone takes it and connects it in a wrong way, or of course there are always strict instructions how to use. Yeah.
If we have connection points for batteries, and you had a question about the future, will be there connection points for supercells? Because you need to recycle them after usage, or.
Yes, that's a good question. Today you cannot go to the supermarket and you don't have supercap collecting point. Then again, we are not using in our devices like one capacitor. But I think the answer is yes. Of course, these have to be recycled the same way as batteries. They don't contain that harmful chemicals, or like lithium-ion batteries, okay, if you damage these, you can get these on fire, but it doesn't happen the same way with capacitors. But of course, yeah.
Okay, thank you. Okay, ladies and gentlemen, I know it's the evening, but the last part for today, we have a workshop for you. And from University of Tartu, Institute of Technology, we have Arko here. And is Veiko coming or? Maybe. Veiko is maybe coming, but we have Arko, and that is already very good. And actually in the evening, starting 6 was there will be a conference right downstairs in the area of competition called Robotex for Space, which are all very welcome to participate.
So, hello, can everybody hear me?
My name is Arko, and they said to me that I have to do a workshop. The workshop was intended for children, starting from the ages from 12 to ending at 15, something like that. But okay, let's do it with you also. As I said, my name is Arko. There should be also Veiko, but unfortunately he has a work interview, so I'm going to do it myself. And today we are having an artificial muscle workshop. I'm from Tartu. There's this lab called IMS lab. It's Intelligent Materials and Systems lab. It was founded somewhere around 2003, and it's in the Institute of Technology. There are around 23 workers, 14 PhD students, and a bunch of other students. We have a lot of different research fields, mostly polymeric materials, also computer simulations, robotics, material science, and so on. So, here we are at Robotex, and we are going to talk about robots. So, what are the major fields in robotics? Firstly, that pops into mind is industrial robotics. You all know those big car companies. Where are the pictures? Yeah, there. They have huge facilities that are full of robots, and they produce something. Also, military robotics. Unfortunately, we don't know a lot about military robotics because they keep it secret. But I've managed to find a robot picture that has guns and stuff. And also, we have medical robotics. And probably medical robotics is the most most interesting or the hardest of those robotic fields, because you're working on a human body, and in medical robotics, there's this golden rule: smaller is better. If you have an operation, usually you use a knife, you have a large cut, then it needs to heal, and there's all those chances that you get infections and so on. And the future in medical robotics is the smaller the better. You have a small cut, it heals faster. I forgot. I have to show my t-shirt. So the university t-shirt. So smaller is better. You will lower the amount of or chance that you can get infections. You don't have so much scarring and so on. But what's the problem with building really small robots? We have electrical engines and motors. We can make it quite small. Does anyone know how small is the smallest motor or usual electrical motors? They are usually like a couple of millimeters, and the ideal thing would be like I have a syringe, I inject some small robots into myself. They will swim around, find the parts of your body that are broken, fix it, and then you will just get rid of the robots the normal way, like the human body does. But those electrical motors, they are too big. It's in the scale of 1 to 2 millimeters, and if you have a robot that swims around, fixes something, you probably need several motors. You need like a gearbox and stuff, so we can't do it with ordinary mechanics or mechanical stuff. So we need something else, and that's the place where artificial muscles come into play. My PhD work is, I'm doing stuff like this. It's a polymeric film. I have a bag full of those films, and the similarity to human muscles is that human muscles react on electric impulses. So does the artificial muscle, but how it's made is completely different, and the working mechanism is also different than the human muscles. But the interesting thing is that when we have an electrical motor, when we cut it in half, what happens? We have a broken electrical motor. When we have artificial muscle and we cut it into half, we have two working artificial muscles, or two working so-called motors. And everything that I'm going to show you today is in large scale. And in large scale, basically, they are useless. Electrical motors and small motors do so much more good work than those muscles. But we can just minimize those muscles and work in small scale. And that's where those muscles come into play. That's the typical geometry. We have it in a rectangular shape. In the previous slide you could see like there was this cut into this film. Come on, play. No. Okay, basically if you try to bend, it works also as a sensor and also energy harvester. Different operating environments. We can use it in water. And we can also use it in air. So basically we have the building blocks to build really small robots. So
because the workshop was intended for children, now I will ask for the, I don't know, someone in front who's the most childish, yeah, or most eager to get their fortune. No? Okay, let's, yeah. So, I'll put the next slide. In my hand I have a fortune-telling fish. Can you please put your hand like this? I will take the fish outside of this plastic bag, put it on her hand, and the fish starts to move. And by doing so, like when the fish is moving the head or tail or something, on the back of this package there's written her moods or fortune or something like that. So, the tail is moving and maybe this way. Yeah, I would say it was moving the head and the tail together, so moving head and tail in love. So I guess you're in love.
Was it the end of the experiment?
Yeah.
Oh, okay.
So now I have this question. Why did the fish move? If I take another fish, put it on the table, it doesn't move. So what's the difference between the table and her hand? What? Okay, the first is heat. Do we have any other ideas? Yeah. Any other ideas? Heat is a good one. Love is a good one. And what? Yeah. So basically, it's cellophane foil. I don't know if you have it, but in Estonia we have those gift wrapping cellophane foils that are really like scratchy, not scratchy, but they make a specific noise. And the fish is made out of this polymer or this cellophane. And the fish is really thin. So if we put this fish on top of our hands are a bit moist. So the moisture goes inside the bottom of the fish. The one side of the fish expands, and because we don't have any moisture up here, or we don't have as much moisture than down on the bottom, one side expands and the other side doesn't. So we can see a movement. And our artificial muscles work exactly with the same principle, basic principle, that one side expands and the other side doesn't. So, I will talk about the working principle. I showed it with the fish, how the fish works, and now how our artificial muscle work. We have a membrane, a polymeric membrane that conducts ion but doesn't conduct electricity. I can show you the sample. Here's something. Just pass it around. On this membrane we have 2 carbon electrodes, and the carbon is very special carbon. It's CDC, the same carbon that the previous talker used in the skull caps. The carbon has electrical conductivity, but still the electrical conductivity isn't good enough for us, so this carbon with gold, so to get even better conductivity. And we have this 3-layer or 5 layers of different stuff, and we put them full of those ions. The red ones are really, really big. They are called cations. The blue ones are really, really small, and they are called anions. And now, when the fish had humidity, we have
We put some potential. The really big red ones go onto one side, and the side expands, and the blue small ones, the anions, go to the other side, and it's basically not the same size. It actually goes smaller, but still. We have a size difference, and that's the reason why we see actuation. That's inside. Here's a scanning electron microscope picture. You can see this part here is the membrane, this polymeric membrane that isn't conductive. Here you see the carbon electrode, and on top of it there's this gold. And the scale is, I would say the thickness is around 2 human hairs. When one human hair is 100 micrometers approximately, then this scale is 200. Okay. Then who's interested, we will have some small experiments, measure resistivity, see the actuations and so on, but let's do it afterwards. Currently it's small scale. We do it in the laboratory, in laboratory scales, nothing industrial. Currently we have this knitting ring, and we put a membrane onto it, and afterwards those carbon electrodes and so on. But it started with hot pressing. We had the different layers, the membrane, the electrodes, and then we sandwiched it all together and just hot pressed it. Currently it's spray painting, and the future is micro printing, like printers that can print really, really small things. And micro printing is basically, I would say, the future towards medical robots and really, really small robots. Here's a video. It's, I don't know, in English it's probably caterpillar, and with these kinds of soft actuators we can mimic nature quite good. If you would imagine when you want to build a robot, like mechanical robot, you have to have like tens or hundreds different parts to mimic this soft movement. But our actuators, you can bend it or wrap it or do whatever you want, and it's mimicking the movement. Show you some examples so you can pass it around also. We also made a race with nature. We put the snail and also a robot that we made. I guess that's the first autonomous robot, soft robot that carries its own weight or the battery with himself. Otherwise they have to use like wires. And currently the snail is still winning. But there's one reason why the snail is so winning. If we have those actuators and we make it really thin, we can have really, really fast movement. But when the actuator has to carry a battery, some electronics and some other stuff, we need to make the actuator really thick so it has more power. But unfortunately making it thicker makes it also slower. And it's slow on macroscopic scale, but on nanoscale it's fast. We also have a robot farm. This one snail robot weighs 830 milligrams, so under a gram. I don't have any like real life comparison to make what weighs under a gram or what weighs a gram. Maybe some rice, like one rice piece. Okay. Do you have any questions? Yep.
Can you tell us more about how have the electricity, so you apply some voltage,
Yeah.
something happens, and then it returns.
Yeah, we have this triple layer or 5 layers of stuff. Here's the membrane. It's not conductive. We put on potential, and the actuator is full of ions, cations and anions. And cations are really big, and anions are really small. We could make it differently, like anions are big and cations are small, but it doesn't matter as long as they have a shape or size difference. So when we put on potential, cations move to one side and the anions to the other side. And because the cations are so much bigger, one side expands.
So you basically add the plus to one side of the element, the minus to the other side.
Yeah, yeah.
And because it is not conducting, there is only potential difference.
Yeah, potential difference, and the anions move to one side or one electrode and the other electrode. I should have some. Let's see if it works. Yeah. We will do it in the workshop also later. But here there's 2 AA batteries and just a simple circuit when you short it or plus minus, and then you reverse the polarities just. So let's put it on. Plus on the one side, now to the other side. That's a pretty dead muscle.
So you just change the
Polarities, yeah. When we change the polarities, minus here, so the pluses will move here.
Will this happen forever? Is there a
No. Chemically speaking, I would say it should happen or work a long time, but in real life, when we apply some potential, we have to have some contacts, and the contacts, the gold or the electrodes don't conduct so good. So basically, more charge is being transferred through here, so it warms up, and at some point it just melts or crashes.
For example, connected to the power outlet, will it flip it really fast?
There's this. We have tried it, and we call it magic smoke that comes out of machines when you don't use them the correct way. Basically, there are some limits of the materials. Those pluses and minuses are ionic liquids. They are basically salts that are in a liquid form at room temperature. So, and those ionic liquids, the carbon and the membrane, that you can't use so high potentials. Also, this is CDC. This is really, really porous carbon, and I'm like 100% sure that there's some water inside it. So if you use it at higher potentials, like over 2 volts, then water starts to hydrolyze. Is it 2.3 or 1.4? For water, yeah. Nothing, but otherwise, yeah, the material is the limiting factor for the potential that we can use. So we can't just stick it everywhere. Yeah.
So there are no ways to make it much faster?
There are. We can make it thinner. We can make it smaller, and then it's much faster. We have a short and it doesn't work. But the good thing is we can just cut the piece where the short is, and we have another actuator. Yeah. So let's start the workshop. The basic idea is that we have different pieces of those actuators, or different stages of manufacturing. There was this one piece that I sent on the rounds. Oh yeah, here. We have this membrane only, and ideally it isn't conductive. Then we have the next piece that is being covered with those carbon electrodes. It should have some conductivity. And the last one is when we have covered those carbon electrodes with gold. Because it was for young children, we have enough of stuff. You can also play around with gold. It's what? We have leaf gold. So I will pass it around also. That's the gold that we use to cover the electrodes. Really shiny. It seems like a huge amount, but ideally, if we could turn it this way and hold it, the human eye can't see it because it's so thin. The visible spectrum for humans is violet is around 400 nanometers, the wavelength. Around, yeah. And this gold leaf is somewhere around 120 nanometers thickness. So really, really tiny. Oh, what else? I don't know. If you're interested in this workshop. Yeah, okay. Put on gloves. Everyone that's interested, come here and let's do it. Ah, yeah.
Going to space, we're taking 1.5 hours.
Who wants to come here?
jah, ma arvan küll, ma ei tea. Ei ole just parim koht töötoa tegemiseks või? So basically we have 5 multimeters. Let's make 5 teams. Mediumid. Naistele meeldivad mediumid, large'id. So, that's the sample without electrodes. Just glass fiber covered with this membrane solution. It's full of those ions or this ionic liquid. Is here anybody who doesn't know how to use a multimeter for measuring resistivity? No, I guess. Just in case. We have those newer Fluke ones, so let's give it here. And you know what's the resistivity sign? It's ohms. Just put it on ohms and measure the surface conductivity of the sample here. Yeah. So that's covered with carbon. You can also touch the gold. It's like so thin. You can roll your finger, but if you rub it, it disappears. It's like only dust. They also put this gold on top onto some foods. Golden one. Siis on üks süsinikuga puudu. Ja kulla
kullaga ka. Saad hästi peenikese. Enne lõikusime neid eelmises töötoas. So have you measured the resistivities? How much? Yeah, yeah. And the carbon one? 25 mega ohms, so it's a lot of ohms. And how much was the one with carbon? 3 kilo ohms. Okay, a lot better.
2.5.
Yeah, and the golden one?
0. Almost 0.
Yeah, okay, almost 0, yeah.
Yes.
Now we have those little boxes that contain batteries and a small circuit. I guess I could show the circuit also, or it's just 2 batteries and a switch, 2 switches. And on 2 of those boxes we have needles. We have to put the actuators in between those contacts. Here you have already a sample in here, but you could also push the needle here. That makes it easier to insert the sample. So you can try it with this one. I don't know if the actuator works. You can probably remove it. Someone tried to cut it. And you have to pass around the needles because we only have, unfortunately, 2 needles. We managed to lose the other ones. Yep.
I have a question. You add some energy into the system.
Yeah.
And you output some energy.
Yeah.
Into the system.
It's basically an ultra capacitor like scale cap does, because we use the same materials. We use this carbon, that huge specific area, and it's also basically the same material. I guess we used Skeleton Technologies carbon for those actuators, and we are using also the same electrolytes inside the actuators. I don't know, you are using ionic liquids or no?
No, then we would not compete on the power level.
Okay. Similar stuff inside. So actually it behaves as a capacitor also, like ultra capacitor.
It's exactly the same logic, just that maybe this ion size difference is something that we don't.
They don't want to have it, because if you have an ultra capacitor that swells and goes smaller, that's a negative effect. But for us, we are trying to have this swelling and crumbling back again, but that we have a capacitive effect, that's just a side benefit. So you can see this really small actuator that has 830 milligrams. It has 150 microfarads per centimeter.
Okay. What are you working on? So you have this.
Yeah.
You have the materials.
Yeah.
From now on.
Yeah.
What's the next step? To make it smaller?
To make it smaller. Yeah, for here, the only reason why we have it in a large scale is just to prove the concept and to show people that actually the things are moving. But going downscale or scaling it down, it's quite hard. Like in the industry, scaling up and scaling down is a hard process. And yeah, there are those applications like biologists use pipettes. And there's a minimum amount of liquid that you can use with the pipette, but you could use those actuators. You have a small capillary, and you can have this actuator like pushing out a certain amount of liquids that otherwise with a mechanical pipette wouldn't be possible. Or you can have like really small pumps that will pump something like a membrane pump
the actuator is moving in and out and pumping really small amounts of liquids. Or lab on chip, like you have a small chip, it has different chemical reservoirs, and you just open one channel, close one channel, so the liquids can move. Like that's the stuff that we are working on. Going smaller and having smaller applications. This thing that we have robots that are swimming inside us, it's a bit of fantasy, but it's cool fantasy.
So how much voltage do you supply here?
2 batteries, 2 AA batteries. This one is 3 volts, but the 3 volts one is quite harsh. It burns out the muscles quite fast. Here we have some resistors inside also, it's 1.2, but I guess it's 2.7 something.
And how much difference is there in the movement extent if you have like 1 volt or 2 volts?
Actually, the movement extent depends how good the conductivity is on the surface. Otherwise, you have the contacts here, and if it isn't conductive, you have the movement only from this side, like where the contacts are. When you have, when the whole surface is conductive, we have a movement all around the muscle. So
I mean, for degradation point of view, then you don't need to apply limit voltage in order to
yeah, when you put higher voltage, it actuates faster, but it also dies faster. I don't know, was it interesting?
Yes.
Yeah. Okay. If you wish, I can give you those fortune teller fishes also. Annan sulle veel või? Okay, thank you. Oleme proovinud ühes asjas patareiga seda, aga see lehtkuld ei maksa mitte midagi. Nad on ikkagi liiga õhukesed ja seal, kui sa paned liigusvara potentsiaali, siis ta sulab sealt läbi lühis. Kuld ei ole piisavalt hea juhtus. Eks ole. Kuld on kõige parem juhtumise käsi, mida me saame seda panna. Aga võiks olla veel parem. Tekivad mingid diviidid. Kas te tõesti kloreerite nii, et teha 10 000 kondentit? Või on ülejäänud mingi muu süümine? Ma ei usu, et ma töötasin 5 aastat seal kloreerida. Nii suutas uskuda. Just mõtlesin, et seega on päris keeruline konkureerida. Nii kallis tootmisprotsess, nii rõve, mitte midagi muud. Jah, saab. Nii.
I missed the part from the beginning.
Yeah.
So the actuation of the metal strip, you have a current that's intermittent that's causing the...
Material we have cations and anions.
Okay.
Cations are really big and the anions are really small. And so when we apply potential, cations move to one side, the anions to the other side.
So one side swells larger and the other one contracts.
Could the same principle be used for like a How long have you been working on this?
Actually, I'm the guy who's making those cations and anions, or they are basically liquid salts, like sodium chloride, the usual table salt that you use in food. Those salts melt at 801 degrees Celsius. So I'm producing salts that are liquid at room temperature.
Oh, nice.
Yeah, and I have those salts, and I add some polymerizable group, so I can polymerize like this cation or anion.
So the other participant is still movable around this polymer, or I'm making those polymers where you can move ion inside.
So is this an engineering project or a chemistry project?
I'm a material scientist. Yeah. Yeah.
Okay. Thank you.
Yeah.
Actually, you can enjoy yourself now for 1 hour because 6 o'clock in the competition stage, first floor, the conference about robotics in space starts, and after that, tomorrow here 12:30. So thank you.
You know. Oh, University of Tartu, huh?